Hello, my name is Li Mingzhen. I'm sorry I couldn't join the conference in Bounder because of my flight connection problem and bad weather and also my bad luck. Hmm. So I would like to make a video representation. I hope I can make our research work can make more clear for someone interested to our research. Okay, so my talk is about develop an audio haptic detect system for the visual impaired person. Here is my representation's outline, and first we will have a look at two research questions. The first one is how to detect different kinds of obstacles for the visual impaired person, and then the next question is after you detect the scenario, how to now visually represent these obstacles to the users. Then the users can make the decision on how to avoid those obstacles. The second part, we will very quickly have a look at the state of the art from the two aspects. Like the first one is optical detect technology, and another one is how to now visually representation of opticals. In the following, I will focus on our method how to develop a 3D DoD system, which consists of a 3D time-of-flight camera and a portable pin-metric displays. We will introduce this later. So we also developed the software and a special design about the tactile optical symbols. Then we will introduce our evaluation work with 6 brand participants in a controlled environment. We compared our system with the normal Vikings in the test. So we will introduce more our findings in the evaluation. Finally, I will make a short conclusions and future work. So the first research question uh, for the detect obstacles. We know every day the visually impaired person will suffer from different kinds of obstacles from the face level or overweight. This kind of obstacles is hard to be detected by a webcam. The foreground-based obstacles is easy, sometimes can be detected by the webcam, but the dangerous job of the obstacles like the horse and steps is dangerous for them, but sometimes it's hard to detect by the obstacles by the webcam. So also a good detector system we think is better not only can work indoor, outdoor, but also can should work in the dark place like at night. Meanwhile, so it's better the system can detect a long distance with a large field of view, so the people can detect a very big views. So what we want to do is how to develop a strong enough optical detect system for the visual impaired person. The next question is how to now visual representation of the obstacles. So the normally the traditional way is like the use the YCAN or some the EAT, ETAs, electronic travel aids. So normally you can detect the obstacles and told you yes there is some obstacles, and then the users have to decide turn left or turn right by randomly. So, and also this kind of system only can told the users only one obstacles and one time. So we are thinking about if they can know the layout of the obstacles in a big or in a large area. Like the sighted person got this information by vision. So what happened to them? So should they can uh, make a route plan and avoid this like the sighted person in advance? So the problem should be how to represent those informations and also evaluation. Let's quickly go through the related work of optical detection system. Since 1960s, the ultrasonic sensors have been used. Yes, indeed, it's low cost and small size, but sometimes it's hard to detect small objects and couldn't get imprecise location and orientation of the obstacles. Then, many researchers work on the infrared or laser-based system. Indeed, it can provide precise location orientation, but it's, the field of view is too narrow, and especially for the laser, it's too expensive right now. And then, the digital RGB camera is also a popular solution in the research world. It can provide a wider field of view, but it's hard to calculate imprecise location orientation. It's hard work in dark area, and also it very depends on the robust algorithms for the scenario. So the next technology to detect obstacles comes to the new 3D depth cameras. There are several different cameras. There are three very common ones. The first one is stereo cameras with at least two digital RGB cameras, and then another one is structure light based, like the Kinect. So different to the Kinect is the time of flight based cameras. It's based on the infrared and send the infrared and get the infrared by pixel. So here are the comparisons of the key features between the three cameras. So we can see the 12 camera will work better. Like the stereo cameras, it's can work in dark place, and the structural light-based camera, it can work outside. So the 3D TOF camera, yes, it can work outside and can work in dark place, and it can have a fast flat rate. It can be up to 80 frames per second, so it can track moving obstacles. So the detect distance is also from 10 centimeter up to 7.5 meters, better than right now the Kinect. So in our system, we use the new TOF cameras to develop our system. The next thing is optical representation technologies. The very popular one is use audio feedback. It can be non-speech or speech-based. This user interface is low cost and simple, but the important thing is little is we are in the field users hearing, especially for the outdoor, and it's harder to give the imprecise location of orientations of the obstacles. Like the voice system, they use the sound signal, the frequency to indicate the distance. So it's a little hard for users to get the exactly the location and orientation. The next thing is to the tactile user interface. It depends on the human beings the touch sensors. So normally people can use the vibrator, belt, vest, and shoot pad, and also it can be used as a pin-match display against the user fingers. The good thing is the tactile user interface it will not interfere the user's hearing and can give some more explicit the location orientation. But the limitation is it need much more sensors to indicate or present more information. Another thing is combine both of them. So come to our methods. So in our system, for the hardware, we use the 3D 12 camera and also use portable pin-match displays. The display has 916 pins. So about the software, we developed the software for the point cloud processing and the segmentation. We also develop a special layout on the tactile display, as well as a set of tactile optical symbols we will introduce later. So, look at the system overview. So we put the 3D camera on at the level of waist. Use the tactile display can touch this while walking. Touch the tactile display while walking. When the users get the warning message, then weekend will be vibrated. Then the users should be stop and check the display to find the layout of the course. And also, if users find the course in 2 meters, the vibrator will work. So here comes the system components. We need a 3D 12 camera. So like this one, it can detect up to 7 meters, but it's a little heavy, about 1 kilogram. But it can work for outdoor. The next is the pin-match displays, like this. It's similar to hyperbaric display, but smaller, with 30 by 32 pins. So normally the free refresh rate can be 5 Hz, but maximal up to is 20 Hz. So it's light, about 600 grams. So the pins can raise up to 0.7 millimeter. Also, we use a wire remote connect with a normal can. So users can use the wire remote vibrator to get the warning message immediately, and also can use the can to detect the areas in 1 meters. So it can be combined, work together with the 3D systems, the optical detect system. And also we need a laptop to run the system and then wireless connect. So basically there's a processing for the point cloud data. So from the real things we need get the deep image, and we need to do the noise filter, and after that we should do the segmentation processing, clustering the opticals one by one, and get the opticals attributions like the distance, orientations, type, and size. The type, like it's hanging opticals or ground based, and or drop off. The size, we will calculate the the width, and the height. So users can know how height of the obstacles and how width. So here comes the representation of the course on the tactile display. On the left side, there is the special layout. The display can render the area in 4 meters, and there is a center reference crossing in the middle. The middle line can indicate the obstacle is in 2 meters or beyond 2 meters. If in 2 meters, it's dangerous for the users. On the right side, we designed the obstacle symbols. So it depends on the different type and the different width and the height. So based on these symbols, users can create some new symbols based on the 3 basic kind. Okay, so let's talk about the evaluation work. So we have an evaluation with 6 blind users, 3 female and 3 male. The mean age of them is 33.7 years old. All of them are good and using wire cans. So the task for the users will with 4 steps. So each participant will spend about 2 hours for for 4 tests. And the first step, users should learn how to learn the tactile optical symbols and learn how to use the whole system. In order to investigate the users have the skills to use the system, in the second steps we have a pre-test. And first we select 6 tactile optical symbols with different type, height, and width. The user should told us exactly the symbols means, the type, the height, and the width. And then we asked the users to locate a ground-based box on the tactile display and told us the distance, orientations. Finally, the users need go and avoid the obstacles. After the 2 steps representation, the prepared, we go to the third part. For the real test, we have 2 test scenarios with different hanging and the ground obstacles. So we let the users walk from the start point to the end point and go through the obstacle zones. We compared the results with normal wire cans and with our 3D DOD system. In the end, we have a short questionnaire about users' feedback. So here is the controlled environment in 2 tests. It's in a big lecture hall about 10 by 16 meter. So we have 12 obstacles, a lot, 3 chairs, a long table, and hanging obstacles, and a box. So in the 2 test scenario, we use the same obstacles, but we have a different distribution. And at the end point, we set up a speaker to play light music to guide the users. Where is the end point? Please have a look at demo video. A short one. Yeah. So normally the blind users use the wire can hard to find the hanging obstacles. like this. So we use a 3D optical detect system to do the segmentation, like this. So here is the pictures of how the blind users can use the system. So like this, when the blind users want to find the orientations of the opticals, they need to touch the display and locating the opticals. Then the user will decide which way to avoid them. So you see, the user turn around and find the way to avoid the obstacles. Here is a very short video. Please check the website to find a full version. So what about the result? Yes, for the first result is how the performance to identify the optical symbols. They have a short training, only 3 minutes to training the optical symbols, and the test on the 6 selected symbols and spend about 2.4 minutes. Interesting is the accuracy right now mean is 87.8. So the user will told us the type, width, and height of the opticals. So for this result, it looks like great. So the second result is how the users locating a grounded box in the pretest. So in fact, we put the box at 11 o'clock and 2.1 meters. So check the right side. The users report the distance orientation here. The mean distance is 2 meters, and orientation is 11 o'clock. Then we calculated the mean distance area. So it's about 23 centimeters. And the orientation area is about 10 degrees. So it's not bad. The users can have vision what exactly the obstacles is. So in the next test, the user can avoid the obstacles. Okay, let's have a look at very interesting result. The detour choose. Normally the user use the Y can. It's hard to say a detour. Check the left side. The user's performance in the router choose in scenario 1. P2 and P3 use the 3D OD system, and others use Y-cans. Then in scenario 2, on the right side, only P2 and P3 use Y-cans, and the other users use 3D OD system. So when we compare these, the 3D OD users and the Y-cans, we can find the Y-can users have a more straight router than the 3D DoD users, because for them, for the Y-can users, they just keep moving to the end point. They don't know how to find a detour. But with the 3D OD system, they can, because they can get the big overview of the scenario. So the next, how about the performance? Other performance in the two real chairs. On the left side is in scenario 1. So the decision point means users will need to detect opticals or the 3D DoD system vibrations. So the users should stop. So this point where the user stop is the decision point. So we can find the users use why can have a more decision point. So with a 3D OD system, the users have the mean point for each router is 2.5, which is lower than the Vikings about 4.83 points per router. And in a t-test, we found it's the the two mean data is significant difference. So let's go to the how about the avoid obstacles. We can find with the why can they hit a lot of obstacles and they couldn't avoid any hanging obstacles on their way. But with the 3D OD system, you can see most of them can avoid the hanging obstacles. But when we compare the spending time, so we can find with the why can the users can very quickly to finish the task, and with the 3D DOD system, they indeed spend lots of times because they need to touch the full screen to check the open space and decide the router. So for the user feedback, they think they can easy to remember the symbols, but the symbols not very easy to find out the difference. They think the center reference grid on the display is help them for the location obstacles. It can easy. It's not very easy to get the distance on the display because they need to calculate. But for direction, they think it's easy to understand left and right, and which clock. And the users think it will be helpful for them to find the layout of the course on the display, and they would like to get the worry messages when some of the course in 2 meters. All in all, they vote the whole system about 4.3. We have still have something need to do to improve it. Another user feedback is we ask them how they exactly avoid the obstacles and how to use the system. They think most of them report and faster than work until get the void messages from the weekend and stop touch the tactile display. They will locate the central grid fasterly and then find out the layout of nearby obstacles. Then he can find a router and walk to avoid this. When they get another void message, they will stop again and do the same things. But we found some of users don't exactly to care about what type of optical symbols. They just care about is there is obstacles and make a void behavior. So what is not good enough for the system? They think there are too many parts and too heavy for the whole system. They would like in the future to make it smaller and to improve the walking speed and can be walk in the real world. So for the short conclusion, we think and first we implement an optical award system with the 3D tube camera and we represent these nearby obstacles on a tactile display so the users can find out the layout. Also, we have a evaluation work. Users can get the spatial relationship between them and the obstacles by the system. Also, users can find a detour with the 3D OD system, which is different to the way we are using a webcam. That's true. Also, users can avoid obstacles, including the hanging obstacles. But the users need much more times and special cognitive load for this. So for the future, we think we can improve this. Firstly, we need more evaluation, indoor and outdoor, for the real scenario. Then we would like to make it smaller by using a smaller camera and also a smaller embedded board. The third thing we can do is how to improve the work speed and reduce the cognitive load. Like the tactile display can use it, but we suggest to use the machine to calculate the detour and inform them in a quickly ways like the vibrator, the left or right. If the users would like to have a look at the scenario, they can check the tactile display. Then we can provide a full function optical detect systems can ensure the work speed and also can provide the users to know what the surroundings. Thank you. Thank you again. So if you have any questions, please send an email to me or you can ask it any questions. I hope I can help and we can discuss more.